Okay, think about your last water bill. What if I told you that you might actually be paying for, well, nothing? Literally, invisible air. Air that is secretly spinning your water meters and artificially inflating your monthly costs. I know, it sounds absolutely crazy, but it is a real phenomenon happening in plumbing systems all over the world. Welcome to This Explainer. I am so pumped to have you here today because honestly, we're going to play detective. We're tracking down two invisible culprits that are actively robbing your plumbing systems. They are stealing your money through phantom water billing, and they're stealing your performance through vanishing water pressure. So get ready because the physics hidden inside the walls of your building are absolutely fascinating.
All right, here is our agenda for the day. First up, the invisible water thief. 2, the physics of trapped air. 3, the 90-degree roadblock. 4, compounding pipe pressure loss. And finally, number 5, optimizing your water system.
So, let's jump right into section 1. The invisible water thief. Investigating the phantom spin. Most facility managers, and really just most of us in general, assume our water bill perfectly reflects our actual consumption, right? Well, here is the secret. Traditional municipal water meters are volumetric devices. That means they just measure the volume of whatever fluid happens to be passing through them. They are completely blind to whether they are measuring liquid water or literally just a gust of wind. If air passes through that meter, it's counted, and you are billed for it, exactly the same as water. To put that into perspective, a 2019 technical report on MagFlow and mechanical meters found something kind of incredible. If a pipe is only 75% full of water because there's a large pocket of entrapped air in there, the meter doesn't just read 75%. It can actually overread by 25%. And this happens because the meter's sensors and turbines calculate the volume based on the high-velocity flow of that air-water mix, basically just assuming the pipe is 100% full of water. You are literally being billed for empty space. Which brings us to section 2, the physics of trapped air, why pressure drops cause volume explosions. Okay, let's dive right into this. How exactly is all this air sneaking into our pressurized pipes in the first place? Well, it essentially comes down to a few documented sources. When the city does maintenance or a water main breaks, air rushes into the empty lines. Or, in areas with intermittent water supply, pipes are emptying and filling with air on a daily basis. And then you have dissolved gases. Just like the carbonation in a soda, oxygen and nitrogen are actually dissolved in pressurized water, and they can form tiny bubbles when the pressure shifts. Think of your plumbing like a giant bottle of soda. When the cap is on, the whole system is pressurized, and the dissolved gas takes up very little volume. You don't really see massive bubbles, but the second you take that cap off or, open a faucet, the system pressure instantly drops. That entrapped gas suddenly expands in volume, effectively exploding into large air pockets. Your meter then measures those rapidly expanding bubbles as if they were solid water rushing past. So, how do you know if your system is harboring this phantom water thief? You've got to look for the physical clues. If your faucets sputter or cough when you first turn them on, or if you hear that noisy banging from a water hammer, you've got trapped air. Even wilder, check your meter when all the water is completely shut off. If the little low-flow dial is still spinning, air is moving through. In fact, a study by the International Water Association showed that when air violently escapes through a meter during a pipe refilling, those dry turbines can spin wildly up to 14 times their maximum overload speed. That is just insane.
Moving on to section 3, the 90-degree roadblock. The second culprit stealing your pressure.
So while trapped air is busy stealing your money, the actual physical geometry of your pipes is stealing your water pressure. We are talking about an engineering concept called minor losses. But honestly, don't let the word minor fool you here. When we look at 90-degree elbows in your plumbing, the resistance they add to your flow is anything but minor. Imagine water racing down a nice straight pipe. It's moving smoothly, efficiently, kind of like a car cruising down a fast highway. But when that water hits a standard, sharp 90-degree elbow, it is forced to make a sudden, abrupt turn. Just like a car swerving at high speeds, this creates massive chaos. That smooth flow is totally destroyed, leading to flow distortion, swirling eddies inside the pipe, and a ton of energy-wasting turbulence. All of that friction translates directly into a drop in your water pressure. Now, what's really fascinating is how engineers actually calculate all that chaos. They use a minor loss coefficient, usually just called a K-factor. Basically, a higher K-factor means more restriction and way more pressure loss. A tight, threaded, regular 90-degree elbow has a massive K-factor of about 1.5. But if you simply swap that exact fitting for a gentler, flanged, long-radius sweep, the K-factor drops all the way down to 0.2. It is literally the exact same 90-degree change in direction, but with drastically less resistance.
Section 4. Compounding pipe pressure loss, the fatal flaw in gravity-fed systems. Let's think about a low-pressure, gravity-fed water system for a second. Imagine a rooftop water tank feeding a building below, where the water is forced to pass through an excessive number of 90-degree connections, all placed in super close proximity to each other. Because a system like this relies entirely on gravity rather than high-power city pumps, the resistance from these roadblocks compounds incredibly fast. By the time the water actually reaches the bottom, all that hydraulic head is completely destroyed and the pressure has vanished into a mere trickle. This is the fatal flaw of over-engineering tight turns in low-pressure networks.
To truly grasp just how much damage a single fitting does, engineers translate all this complex fluid dynamic math into a really simple real-world visual called equivalent length. Equivalent length simply asks, how many feet of perfectly straight pipe would cause the exact same amount of friction and pressure drop as this one specific fitting? It takes complex K-factors and turns them into a measurement we can instantly picture in our heads. To put that into perspective, let's look at a standard 4-inch pipe. If you install just one sharp-edged 90-degree elbow, it chokes the flow exactly as much as adding 15 extra feet of straight pipe to your system. Let that sink in for a second. A single fitting is mathematically identical to dragging your water through an extra 15-foot detour. But if you use a gentler sweep elbow instead, it only adds about 6 feet of equivalent length. Every single tight fitting in your system is an invisible detour slowing everything down.
But here is the absolutely crucial point. What happens when you start chaining these fittings together? Well, if you space fittings widely apart, say more than 10 pipe diameters, the turbulence has time to settle, and you just add up the losses normally. But if you cram multiple 90-degree connections in really close proximity, the turbulence from the first fitting hasn't even dissipated before the water smashes into the second fitting. The friction effects actually compound and multiply. You literally have to multiply the total pressure loss by up to 1.25. In tight plumbing closets, this compounding effect absolutely destroys whatever hydraulic pressure you had left.
All right, Section 5, Optimizing Your Water System, Engineering Solutions for Flow and Billing. Now, we aren't just going to leave you here with vanishing pressure and ridiculous water bills. Whether you are a commercial facility manager dealing with thousands of dollars in overbilling, or just a homeowner who wants a better shower, there are concrete engineering-backed solutions derived straight from our source material. Here is a 3-step action plan to optimize your plumbing layout. Step 1, install air release valves, or ARVs, at the high points in your system. These act like a vent, allowing trapped air to safely bleed out before it ever has the chance to reach your meter. Step 2, add a smart valve upstream of your meter. This physically stops the pressure drop from traveling backward, preventing that whole soda bottle expansion effect that causes meters to overspin. And Step 3, review your pipe layout and swap out those restrictive, tight, regular elbows for long radius sweeps. This will drastically cut down your minor losses and win back your water pressure.
To wrap things up, I want to leave you with this final, powerful thought from our sources. You aren't just paying for water, you're paying for air, and your pipes are making it work harder to reach you. The physics happening behind your walls are completely invisible, but their impact on your wallet and your daily comfort is incredibly real. Next time you open a sputtering faucet or stare down a surprisingly high utility bill, I want you to ask yourself, what unseen physics are actively costing you right now? Thank you so much for joining me on this explainer, and keep questioning the mechanics of the world around you.